Hello everyone and welcome to this very important discussion about digital elevation models and different types of resolutions. As you know that digital elevation models are storehouse of information. Theoretically n number of derivatives can be generated using digital elevation models, and so far about 20-30 derivatives are already in application part, and many of them we would be discussing. But before that I thought that let's discuss further intricacies about digital elevation models, because like satellite images, DMs are also very important input in any GIS operations nowadays, because everywhere people are if they are working on a terrain, then they have to employ the digital elevation model. So, this part I discussed little bit in the previous discussion about the spatial resolution, but here we are going to have more deeper discussion on spatial resolution, and we will see how through examples that how we can differentiate which is better and which is not so good. But overall what I have said that also I have been saying that each resolution data is important, whether it is a 1 kilometer resolution data or 30 kilometer resolution data or 30 centimeter resolution data, because the application area of different spatial resolution data is going to be completely different. So, they are complementary to each other, and but nonetheless we must understand what is basically spatial resolution when we talk. So, in case of satellite images, what we say that it is measure of how closely pixels can be resolved. So, if if we can resolve that those pixels in an image, and that becomes the resolution of an image. And of course, it will depend on the properties of the system which is creating the image. Basically, it is the precision of that sensor which is generating anyway. But why we are discussing of satellite images, because as you know that nowadays there are various techniques of generating digital elevation models which are based on completely on satellite data, like stereo pairs, like SAR interferometry, or like LIDAR, or like your thermal infrared data. And therefore, there is a close relationship between remote sensing or concepts in remote sensing, in digital image processing, and also in GIS. Now, as you know that in a simple terms, if I want to say about spatial resolution, that means the clarity which I am having in the image or in my digital elevation model. So, this clarity basically decides by its spatial resolution. Generally, what we have observed that high spatial resolution satellite images will be more clearer than relatively coarse resolution satellite images, and same with your digital elevation models. Now, in remote sensing, as you know that resolution means the resolving power, how closely these can be resolved, the pixels. Here, how closely the cells in case of DEM, which is again a raster, a grid form, and how cells can be resolved. So, and this resolving power will allow or improves our capability to identify the presence of two adjacent objects very clearly. If a resolution is relatively poor, then those two adjacent objects may not be distinguishable. Now, the condition also here is that these two adjacent cells or pixels should have very distinct properties. Then it becomes much easier to identify two adjacent objects. But nonetheless, this resolving power will allow us or will create the capability to identify the presence of two objects. Further, this capability is basically, as I have said, depend on the properties of two objects. So, DEM which we are discussing shows that finer details is said to be finer resolution. So, when we can identify small changes in elevation or in terrain through a DEM, we say is a quite good high-fi or fine resolution or higher resolution DM compared to a coarser one. But this is always in relative terms. Earlier, as said in the previous discussion, that NOAA AVHR stands for Advanced Very High Resolution Radiometer, but it is no more now high. So, at that time it was high. So, relatively that was high, but relatively now, since we are having 60 or 40 centimeter satellite images, and in that term that is not high. So, it is this, whenever we say coarse resolution, fine resolution, it is always in relative terms, relative to some some resolution. Also, we briefly touched about two types of resolution which exist in satellite images, in DM, sorry. Whereas in satellite images there are 4 types of resolution exist. So, here we are not discussing satellite images resolution, we are discussing about the resolutions which are associated with the digital elevation model. So, first is when we say spatial resolution, generally what we mean is the horizontal resolution, and which is the spatial frequency at which the samples are taken or modeled, and basically it is in that sense it is the size, cell size in x and y direction. And as you know that this in a raster format, and the cell is always square. So, x and y are going to be the same dimensions, whether it is a 10 meter, 20 meter or 100 meter, and this is being equal, and thus cell always being square. However, remember also that overall shape of a raster or a grid or a DM can be either square or rectangular. The second type of associated resolution with the DM is called vertical resolution. Basically, this is the least count. So, this DM, in which we refer how frequently the DM can record a difference in elevation. Often this is a integer meters or feet. So, generally we talk nowadays, most of the digital elevation models which are available free of cost, the cell values are in meters and in integer values. That means they are in whole numbers, you do not have decimal or fractions or floating point. So, that means the least count there is 1, maximum 1 meter, and that is why the vertical resolution there is 1 meter. And I also mentioned that it is need not to be the horizontal resolution and vertical resolution same, and generally horizontal resolution is relatively less as compared to vertical resolution. Like if I give example of SRTM 30 meter resolution, so horizontal one cell is representing 30 meter by 30 meter ground area, but vertically each cell can have at least 1 meter of variation and 2 adjacent cells, or that is the least count in that sense. So, vertical resolution is often higher, that is because the value is low here, more fine than horizontal resolution. Now, DM spatial resolution alone does not determine the accuracy. This is a very important part, and many people get confused. Sometimes they use these two terms, accuracy and precision, synonymously, but they are completely different terms. So, accuracy basically is a statistical concept or a statistical term, and which states that likelihood or probability that a particular set of measurements are within certain range of true value. So, you are having some true value or standard value when you compare your measurements, and how close your measurements are. If they are very close, we say highly accurately measured. But if there is a very large difference between the standard value or true value and your measurement, then we say it is having poor accuracy. However, the precision is a statement of the smallest unit of measurement to which data can be recorded. That means precision depends on the instruments which I am going to use. Suppose I am having a 1 foot scale, on one side I am having inches, another side I am having centimeter. Now, relatively this inches side is having poor precision or less precision as compared to my centimeter side, because as you know that in 1 inch, I can have 2.5 centimeter or 25 millimeter. Whereas if I make divisions in the inch side, maximum I can have 10 divisions, and here I am having 25 divisions, and therefore the precision of centimeter scale is relatively higher than inches scale. So, same with the satellite. If a satellite is acquiring data at 30 meter spatial resolution, another one is acquiring at 3 meter resolution, definitely the precision or spatial resolution there is much higher in case of 3 meter. So, this or whatever is higher spatial resolution. And so, what the point was that DEM high alone does not decide the accuracy. That it is not always true that high spatial resolution will have always accuracy, because as I have already explained, accuracy is a statistical concept. So, I may be having a spatial resolution of 5 meter spatial resolution DM, but the elevation values which it is giving may have a large difference between my standard true value than compared to what this digital elevation model is giving. So, it is not true that high spatial resolution digital elevation model will also have a better vertical accuracy. So, this one has to remember. So, final resolution DMs may offer great precision, but not necessarily they will have a greater accuracy. So, because these two different terms altogether, one depends on how closely we or how nicely we do the measurements, and the precision is based on an instrument or tool which we use to measure certain things. This measurement may be the length measurement, this measurement may be a reflectance measurement or any other measurement. Now, further, if we see that for a sensor, a satellite based sensor with a 10 meter spatial resolution may suffer from systematic bias, noise or other random errors, and which may be less accurate than a 1 kilometer grid. So, because you know that satellites are moving objects, and some satellites or that it was not moving in a design orbit, it may have all these errors, systematic bias, noise or other random noise. And if I use that data to generate a digital elevation model, I may not have that kind of accuracy as compared to a more data which has been acquired by a very stable platform, though spatial resolution might be relatively coarser. Examples, how do you feel about high spatial resolution or low spatial resolution? Here these are of course the simulated images, but the real one I will also show. So, here the one cell is representing 110 by 110 kilometer area, and as you can see that it is a completely blocky, jagged kind of appearance, and it is very difficult to resolve two pixels easily or two cells here easily. If I go little better towards the better side of spatial resolution like 30 kilometer by 30 kilometer, then I start seeing some pattern, but still it is not that easy. But however, if I go for 1 kilometer resolution DEM like this one or a satellite image, I start getting the pattern very easily. So, when we move from coarser resolution to higher spatial resolution, definitely it is more comfortable for our eyes to resolve these two cells which are adjacent to each other, and therefore they are more comfortable to read and make some interpretation out of that. Another example is given here, that here the matrix is 1 by 1, and of course that is the unit cell, and a cell is a unit, it is indivisible, we do not see any variation within that cell. But when we go 2 by 2, then we are seeing at least 4 different shades of that blue color which we are seeing, and we keep moving like this. As soon as we come to this location 10 by 10 or 20 by 20, the letter R start appearing. So, at this stage still there is a doubt whether it is a 8 and whether that is a or R. But once we improve the resolution, Instead of 1 by 1 or 2 by 2 or 10 by 10, we go for 20 by 30. So, number of cells are increasing, and this is what exactly happens in case of your cameras, digital cameras like in mobile. When you move from 5 megapixel to 10 to, and now there are cameras which are providing resolution of 44 megapixel. So, very fine details you can have through those cameras or capture those fine details. So, as soon as we enter here in the 20 by 20, then this letter R start appearing clearly, and of course, then you keep moving, but recognition of that letter will not improve, except that it might look more sharper and sharper. So, that means this, for in this particular scenario, the 50 by 50 is more appropriate or optimized resolution to recognize such objects. So, that is why I said that always it is not good to go after always higher and higher spatial resolution. Another example here is that comparing what we are comparing small versus large cell sizes, and what we see here is a polygon, but when this polygon is converted to raster and that too is 16 by 16 cells matrix, this is how the boundaries will appear. They are completely jagged and stair steps case kind of thing. But when we bring at 8 by 8 cell, they are further deteriorated, and when we are bringing at 4 by 4 cells, just you are seeing. Now here comparing this, the rightmost one and the leftmost one, see the input polygon had so smooth boundary, and this 4 by 4 cell one is having very poor representation of that polygon. So when you move from higher to lower, this is what happens, that is smaller cell size here, for here the 73 meter resolution 16 by 16 grid in this example. Here the cell size has increased, that is 80 square meter. Then higher resolution, of course this one relatively, this is lower resolution, higher feature spatial accuracy, lower feature spatial accuracy. Of course, because number of cells are more, therefore it will take more time to display as compared to the less number of cells in the rightmost example. Slower processing, faster processing, large file size, smaller file size. That means both, if I take this one and this one in example, then both are having some advantages or disadvantages. So, it depends what are our requirements, targets for projects, and scale which is we have to produce the result in GIS. So, if we can decide, then we can also decide that which resolution data I have to employ, because now choices are increasing even for the different spatial resolution DMs. 30 meter 3 choices are there, but less than 30 meter few choices are there. At 1 kilometer again you are having few choices, at 90 meter not many choices. So, depending on our requirement, projects, targets, we should choose very appropriately the spatial resolution. I am repeating again, it is not always good to go always for higher and higher spatial resolution, because if you go for higher spatial resolution, then what you are going for slower processing, large files and slower display as well. You may or may not achieve high accuracy, because that part we have already discussed. Similar thing here, that when cell is very small, and then you are having a higher spatial resolution relatively, and when cell size is large, like here it is 8 meter, then you are having a coarse spatial resolution. So, it depends the area of the cell which is representing the ground. If it is represent a single cell is representing the large ground area like here, then it is having coarser resolution as compared to this one which is representing a small area. In case of satellite images, visually you can see very well that this is these two images are covering the same area, but one is having pixel size or spatial resolution is 15 meter, and here it is 15.4 centimeter. There is a change in the units. So, be careful. This is 150 centimeter and this is 15.24 centimeter. Means there is a huge difference, 10 times difference between spatial resolution. and obviously which is being and therefore these cells, these pixels are getting dissolved and you are getting a very good quality picture or satellite image here as compared to in this one. So, for many cases higher spatial resolution may be very beneficial, and there are other requirements might be there in your project like scale. This scale has to be, if I am working on a 1 raised to 2500 scale, then definitely I need a higher spatial resolution and satellite image. But here a spatial resolution in this example is the same, scale has changed for the same area, and of course the effects are there. So, effect of increasing the scale with the constant spatial resolution, there will be definitely different results. Now, the thing is, if I have to produce my results at 1 raised to 50,000 scale, then why I should use this 60 centimeter spatial resolution? I may resort and may compromise on spatial resolution, because ultimately I have to produce my results at 1 raised to 50,000 rather than at 1 raised to 250,000. That was the purpose of showing this one. Now, DEM we have already discussed, so just for completeness I would repeat that part. They say ordered array of numbers that represents the spatial distribution of terrain attributes, and when we say DEM, the middle letter, the E is for elevation, but this E value can be replaced with other properties also, and basically as you also know that DEM represents the spatial distribution of elevation above some arbitrary datum in the landscape. Generally the digital elevation model, typical digital elevation model which we use are representing elevation values above mean sea level, and these surfaces, and these are continuous surfaces, and can also represent if the property is not elevation, the cell value is not elevation, then we can replace that value with groundwater levels, chemical qualities of soil or water and other things. This is again very typical example of a digital elevation model being displayed in grayscale, and the range, elevation ranges are between 95 meter to 70 meter. Lighter, generally this is how people prefer to display the higher values, higher elevation values are always given the lighter color or lighter tone as compared to the darker one. So, this is the standard way of displaying digital elevation model. Just looking this digital elevation model, one can have the feeling of the terrain, and not only that but also by looking these elevation values minimum and maximum, that will give you a feeling that roughly in a 50 by 50 kilometer area, one can have values varying between 95 to 30-70 meter. Sources of DEM which we have already discussed, so this part I am skipping here. Lot of discussion will also take place in future about different resolution DEM depending on what derivatives we are going to have. So, the only point which I want to bring here, that when we substitute voids with low spatial resolution cell values from those DEMs, then will we be driving or creating some output from those digital elevation models which are void free may provide some problems. So, therefore, it is very important. That is why this discussion is again here, is that because you this SRTM 90 meter resolution wise it is higher, but it had the voids. Now, the voids have been filled, but these have been filled by 1 kilometer resolution, and therefore, when I use such a void filled 90 meter SRTM DEM and drive some parameters or derivatives, then I may have some problems. And resolutions part we have already discussed about like different one, like for example USGS DEM, it has the resolution or spatial resolution 1 kilometer, and whereas the vertical resolution had 100 meter. But nowadays this SRTM DM or Ester GDM or Cartosat DM, they are having much higher spatial resolution vertically as well as spatially. This example I am again bringing with a different discussion here, that this is the USGS DM of 1 kilometer, this is a 90 meter, again this is Boyd field, and you see the results, you can compare. The seam is a little problem here, and this also we can wrap up by now saying that spatial resolution basically is the ability to distinguish closed space objects on an image, whereas in case of satellite images there are 4 resolutions. Spatial resolution is common both in satellite images and DM, whereas in case of satellite images we will have a spectral resolution, and because we are using satellite images to generate digital elevation model, so it is also necessary to know about that. So, this basically depends on where our bands are located and what is their width, and the sensitivity of a chosen lambda band means where they are located in EM spectrum, because at different locations the sensitivity is different, and generally like thermal bands are having very broad width as compared to visible or infrared. So, that will depend. High spectral resolution means for a same part of or for a small part of electromagnetic spectrum, I may be having many bands as compared to having less number of bands. For example, if I give example of Landsat MSS and TM, then relatively TM had less spectral resolution as compared to TM, ET or MSS. So, MSS had the less spectral resolution, whereas TM or ETM plus had or OLI are having better spectral resolution. Another term of among resolutions in remote sensing data, which is called the temporal resolution, basically is that repeativity, how frequently that satellite visits the same area, that is the time between observations. So, that is also very useful, particularly in change detection studies or monitoring something. So, this will again depend on the spatial resolution. Coarser the resolution, higher the temporal resolution. That means there is an inverse relation between spatial resolution and temporal resolution, because coarse resolution means the path, the swath is much wider, the path is also wider, and it will cover a large area. So, therefore, it can revisit the same area maybe twice in a day, in case of like NOAA AVHRR data, which is having 1 kilometer spatial resolution. But a satellite like IKONOS, which is having 1 meter resolution, will visit that area maybe after 30 days, 40 days, and the swath width is only 11 kilometer because of that. So, there is an inverse relation between spatial resolution and temporal resolution. Higher the spatial resolution, poor the temporal resolution, and vice versa is also true. And the last one among these resolutions in remote sensing is radiometric resolution, that is nothing but the precision of observations. And remember, this is not accuracy, because these are two different terms, precision and accuracy, which we have already discussed. So, no more confusion about. So, how accurate, how precise your observations are depending on the instrument, that is the sensitivity. So, if it is recording at 8 bits and another sensor is recording at 12 bits, 11 bits, then radiometric resolution of 11 bit is higher compared to 8 bits. For example, our IRS 1C, 1D, they were recording like PAN data at 6 bits resolution, radiometric resolution, and whereas the in other sensors panchromatic data was being recorded at 8 bits. Like in case of NOAA AVHRR, the radiometric resolution is 11 bits. So, it is relatively higher. So, a sensor which may have a spatial relatively comparatively poor spatial resolution, but may have high radiometric resolution and also will have high temporal resolution. So there is a always trade-off between resolutions. You gain something, you lose something, and it depends on our requirements and projects. Accordingly, one should choose these resolutions. Further, as we are discussing in context of remote sensing, because four very well established techniques of generating digital elevation models are remote sensing based. So therefore, it is worth discussing that effect of an optical instrument, which are generally used like stereo pairs data also used, which making in a separate part of an object distinguishable by the eye. So that will depend of course on your spatial resolution. And more widely, the act, process or capabilities of rendering distinguishable the component parts of an object or closely adjacent optical or photographic images. So basically, in a nutshell, what we can say about, especially about the resolutions and particularly about the spatial resolution, more the clarity I get in my images, I get better resolution. So with this, I end this discussion. Thank you very much.